For centuries, classical physicists like Isaac Newton pictured reality as an empty void, an inactive 3D box where objects simply happened to exist. In that classical model, time operated entirely on its own. It was a universal metronome, ticking forward at the exact same rate for every person, planet, and star in the cosmos, completely unaffected by what was happening inside the box. This view dominated early physics because it matches our everyday human intuition. We experience space as a passive stage, and time as an independent timer. But in the early 20th century, Hermann Minkowski and Albert Einstein showed that space and time are physically fused together. They revealed a four-dimensional continuum known as spacetime. Reality wasn't measured by a location on a spatial grid anymore, but by events, specific points defined by 3 spatial coordinates plus 1 time coordinate. But combining these two properties creates an immediate mathematical problem. Distance and time are entirely different physical concepts. You measure space in meters, while time is measured in seconds. Merging spatial meters and temporal seconds into a single equation sounds absurd. To actually understand the mechanics of reality, we first have to figure out how the universe bridges that gap, mathematically translating a physical distance into an elapsed duration. Look at this graph showing a standard 2D coordinate plane. If we want to figure out the distance in regular physical space between point A and point B, the math is straightforward. We map out the x and y dimensions and apply the Pythagorean theorem. By squaring the x and y coordinates and adding them together, we get c squared, the precise physical distance between the 2 points. Notice how drawing a curved or zigzag line between these same 2 points increases the numerical distance traveled. In standard geometry, a straight line is always the absolute minimum possible distance that you can travel between 2 points. Now, let's transition into spacetime by swapping the y-axis for a lowercase t. Here, we treat points A and B as events, moments in time mapped to specific points in space. Einstein proved that time is relative. When an object increases its velocity through space, the passage of time on that object slows down relative to everything else. Because moving faster through physical space effectively steals from your progression through time, these coordinates have an inverse relationship. To calculate the time you actually experience, the variable e, you must use subtraction. The formula becomes e squared equals t squared minus x squared. That minus sign means that the more a traveler moves through physical space, the x variable, the less elapsed time they actually experience on their own clock. This inverts the rules of geometry. If you take a wandering zigzag path through spacetime, you spend your budget on spatial movement and experience less time. Standing perfectly still in space results in the longest possible duration. Minkowski's math correctly predicts how reality operates, but we still have an unresolved mechanical problem on the chalkboard. How do you mathematically subtract a spatial distance in meters from a time coordinate in seconds? This unit conflict is resolved by a constant physical reality, the maximum speed of the universe, the speed of light. In basic physics, multiplying any speed by an amount of time gives you a physical distance. By multiplying our time coordinate, t, by the speed of light, c, the math perfectly converts those seconds into a distance measurement, specifically light seconds. The speed of light functions as the structural bridge between these dimensions, defining the rate at which time translates into distance so they interact within the same equation. We now know that our reality operates on a specific grid of 3 spatial dimensions and 1 time dimension. Why is space-time locked into this exact configuration? If we stress test the math by adding a second time dimension, the mechanics of cause and effect break down. Extra time dimensions allow for closed time-like loops. This allows effects to happen before their underlying causes, generating unresolvable paradoxes that shatter the timeline. Adding an extra spatial dimension creates an equally severe physical failure. In 1917, Austrian physicist Paul Ehrenfest calculated how gravity would behave in a 4-dimensional space. Ehrenfest discovered that simply doubling the distance between a star and a planet in a 4D space causes the gravitational pull to drop off by a massive factor of 8. Even tiny variations would cause planetary orbits to fail, sending them spiraling into their suns. Adding extra dimensions of either space or time triggers catastrophic mathematical failures that would physically destroy the universe. If we reduce the dimensions to a 1 or 2-dimensional flatland, the available geometry becomes too restrictive. Atoms wouldn't have the necessary spatial freedom to form complex bonds, making biological life impossible. This rigid 3+1 geometry represents the absolute minimum complexity required to support chemical evolution, and simultaneously the absolute maximum limit before orbits become gravitationally unstable. Spacetime is not an arbitrary, empty backdrop. Its mathematically unforgiving 4-dimensional geometry is the exact and only reason a stable universe and humanity can exist at all.